So in my previous video, I demonstrated how I tuned this quarter wave cavity filter to the US APRS frequency, which is the 144.39. We used the transmission loss method, wherein the output from my spectrum analyzer's tracking generator was fed into the input of the cavity filter, and then the output of the cavity filter was then fed into the RF input of my spectrum analyzer. And then we used the frequency response graph to tune the cavity filter by moving the coarse tuning plunger and the fine tuning plunger to that frequency. We also made sure that the frequency band pass was quite narrow, so that we tried to contain or curtail the what passes through the filter and what gets rejected. We tried to make sure that the frequency, the resonant frequency of the cavity filter was 144.39, and we did our best to zoom in on the frequency response graph, so that we are right at that 144.39 meeting point, which is fine. I think that's a good way for tuning a cavity filter. But there's also another method for us to double assert that the cavity filter is in fact right on the nail at that desired frequency of 144.39, and that method is called the return loss of the cavity filter. So before we go to the return loss method, I want to quickly show you, just to refresh our memories, how the frequency response was from the previous transmission loss method we implemented in tuning this filter. So let me switch the visual to the spectrum analyzer, and let me show you exactly what we saw in our previous video as the output. Okay, so what I have here is I set up my center frequency to 144.39. We have a 500 kilohertz of span. So let me turn on my tracking generator. So let me actually step back a little bit just so you can appreciate what we are seeing here. I'm going to switch it to 50 megahertz for now. At the outset, you can tell that we are at right on the nail with the 144.39, and the marker is showing 144.39 in here, which is great. But really, to double, triple check, we really need to zoom in on that peak and see exactly where we are in line with that 144.39, whether we are tuned properly, etc. To do that, we will go back into span. This time I'm going to change it to 500 kilohertz. Now, once you zoom in that close into the frequency response, you can tell that it's quite flat, obviously. But the bigger concern for me is this section here. It seems like there's a peak right at that point. However, we are tuned, the 144.39 is tuned at that location. So we need to move really to be 100% precise with our 144.39 tuning. We need to move this peak to match with the marker. Right now it is a few, maybe 5 kilohertz short of that precise tuning and resonance. So this one way to do that is go back to our cavity filter and readjust the fine tune plunger and move this guy over toward the right and make sure we are tightly aligned. We should have done this I should have done this in my previous video, and I did not do it. I honestly missed it and did not even remember I should do that. In any case, let's try to use this video as an opportunity to do that, not through the transmission loss method, but rather the reflective loss method. Okay. Now, in a reflective loss method, you will probably need a device, a test measurement device, such as a network analyzer or a VNA, which can help you measure not only the transmission loss but also the reflective loss. But I don't have access to a network analyzer or a VNA. However, I do have access to a directional coupler made by Mini Circuits, which we can leverage in this experiment. I'm not going to spend time on explaining what a directional coupler is. There are several videos out there that explain. W2AEW has a fantastic video where he talks about directional couplers and how they can be utilized in various RF related projects. In fact, he has a video that covers exactly what I'm trying to cover here. So in this scenario that we are working on, we will feed the spectrum analyzer tracking generator's output into the out port of the directional coupler. We will take the output coming from the input port and feed that into the cavity filter's input port. Okay, and then we'll take the coupler's port or couple port and then feed it into the spectrum analyzer's RF input port. Okay, so the idea is that when you transmit a frequency through the output port, if the input end point is tuned to the proper frequency of that frequency, that is, then there will be minimal return loss. It's almost like an SWR meter. Let's say you, as an example, if you had a 2-meter antenna on this end of the input port and you fed through a 144.39 frequency, if that antenna is tuned to that 144.39, the reflected loss will be minimal coming out of this coupled port. So that's the idea. If the antenna is not tuned properly to that 144.39, there will be a notable loss that is realized by the coupled port. All right, so that's the high-level summary of what this idea is based off of. So let me get this set up quick, and I'll be right back. Okay, so I wired up the equipment here. Let me quickly walk through what I've done here. So right here we have the directional coupler. As mentioned earlier, the output from the tracking generator is fed into the coupler's output port, and the input port is hooked up to the cavity filter's input port. I've also terminated the cavity filter's output port with a 50 ohm dummy load. Last but not least, I've connected up the coupled port to the RF input on the spectrum analyzer. So let's switch our camera view to the spectrum analyzer now. Okay, so now we have the the return loss set up, ready to go. I have my spectrum analyzer set up with the center frequency of 144.39. The marker is also moved to that center frequency. I'm spanning at about 10 megahertz, and we will zoom in. And I haven't turned on the tracking generator quite yet. But before I do it, I want to call your attention to some of the characteristics of a return loss frequency response. In a return loss setup, the frequency response is plotted with a dip rather than a peak that you saw in the previous method of transmission loss. In a return loss, when there is a dip, it means there's minimal return loss, meaning the endpoint is resonant at that frequency. In this case, our cavity filter is resonant at that frequency. On the other hand, if the cavity filter is not resonant at that 144.39 frequency, the dBm value would be much higher. So and that'll provide us a visual of tuning the cavity filter. So let me turn on the tracking generator. As you can tell, let me turn on the marker. As you can tell, we are at about 10 megahertz span, and our center frequency is 144.39, and which is fine. However, as we discussed earlier, we are zoomed out quite a bit. For us to make any sense of this alignment with that peak, we need to zoom in further down. Before we do that, again, as I mentioned earlier, keep a note on this dip, meaning your cavity filter is resonant at that frequency. Now we need to go further down and further zoomed in to make sure that we are tightly aligned at that 144.39 downward dip, or the peak at that downward dip. So I'm going to go to span, change the value to, let's say, 5 megahertz, which takes it even further down. I'm going to further go down. Let's change it to 1 megahertz. And now you can start to see that we are not all that aligned after all. If you can see, the cavity filter is tuned at that peak down there. However, the center frequency is right where the marker is, which tells me that we still have a little bit of fine-tuning to do to push that downward peak toward where the marker is, so that the marker and the downward peak are in lockstep and tightly aligned. So this is a great example of why a return loss would be a better way to gain a closer look at that peak than the transmission loss. So let me further go down. I'm going to change the span back to, let's say, 500 kilohertz. Again, this is going to further amplify where we are misaligned. I'm going to go to 250 kilohertz. And if you can see now, our marker is here, but however that peak is right about there. So let me go back to, let's say, where were we earlier, 500 kilohertz. I'm gonna tune the cavity filter. I'm gonna adjust the fine-tuning plunger a little bit so that we get closer to that alignment. All right, so what I'm also going to do, go into my marker function and turn on the track the marker and make sure we are tightly aligned at that Actually, you know what, let me turn it off. I'm going to move the marker to 144.39 megahertz. All right, and then move that to the center frequency. Okay, now let's gently move the fine-tuning plunger inward so that that peak is right at that bottom there. Okay, so I think we adjusted our fine-tuning plunger closer to, we moved our downward dip peak closer to the 144.39. But the bigger question is, are we close? Are we in lockstep at that frequency, at that peak? That's what we need to double check, triple check right now. I'm going to go into my span again, change the span to, let's say, 200 kilohertz. Let's see. So at 200 kilohertz, let's see if I can zoom that in a little bit. Okay, so at 200 kilohertz, it looks to me like we are in a good position, meaning it's hard to tell. I think at that zoomed in level, we are very close and tightly aligned. I think our markers are also showing the frequency, but let's see if I can move this marker. See, if I move the marker, you can watch here that's moving toward the left. So I think we were at the right level earlier. All right. Well, hang on. Frequency 144.39. Oh. And okay, I think we nailed it. We can further zoom in, let's say 50, or actually hang on, 100, no, hang on, span 100 kilohertz. And let's go to marker and the frequency. I think we are nailed in, so pretty good. So in any case, I wanted to show you the return loss method if you are venturing into tuning a cavity filter through the use of a directional coupler like I have here through a spectrum analyzer with a tracking generator. Now, before we close, I want to show you something very interesting, and I find it very useful in my own learning experiences. I'm going to zoom back a little bit on my span. I'm going to go back to, let's say, 50 megahertz. And let's actually go to 1 megahertz. Okay, so that's the, let's keep it at that level. So that's a return loss. I'm going to go to my trace and hold B. All right. And what I've done there is I've held this visual into a B slot, so sort of like a storage memory, so we can reference this visual at a later time. I'm going to go back to my tracking generator, turn off the tracking generator for now. But okay, so what you're seeing now is the output from the trace hold. This is not real time. What you're seeing is the snapshot. But I'm going to go back to trace. Earlier on, I had saved in the A slot, I had saved the transmission loss snapshot, and in slot B we have the return loss snapshot. Now, as you can tell, in the transmission loss we were off a little bit. This was before we readjusted right now. So actually I forgot to tighten the lock nut on the fine adjuster. Anyway, so you can appreciate, if you were to compare, contrast the transmission loss before and the return loss after tuning, you can appreciate the value of having that capability of a transmission loss method and a return loss method, and also to be able to reference both of those graphs through this feature in this spectrum analyzer called Trace. I wonder if I can go back to my span and go to, let's say, 25 megahertz. Okay, that doesn't make any difference because this is a snapshot. Okay, that's fine. I hope this was useful, and I hope this was intriguing. And again, I'm no expert when it comes to duplexer tuning or cavity filter tuning, or even the use of spectrum analyzer, tracking generator. I'm learning in this process, so this is definitely a learning thing for me. And many times I get asked, hey, why do you use these? Why do you make these videos? To be completely candid and transparent, I don't do these videos for YouTube financial reasons. I don't do these videos for that purpose. I primarily do these videos for my own references. If it helps others, fantastic. That's a blessing to have. But I primarily do these videos for my own self-reference material, so that I can go back to those at a later point in time, or even point people to it when they ask me for any pointers or tips or whatever. So these are essentially for my own reference, for my own edification, if you will. So with that, thank you so much for watching, and we'll talk soon. God bless.